everyone. Welcome to the nanobubble generator training for institutional water systems. Today what I'm going to do is walk you through an entire institutional water system. We're going to talk about what kind of stuff is in the water, what kind of stuff we can do with nanobubble generators, how you would install the nanobubble generators, and kind of what it's going to look like when you start these nanobubble generators up. We're going to give you some real-world examples and show you some actual results from what nanobubbles can do to help in domestic water systems. This video isn't going to cover every single type of system, but it does go along with that diagram that I sent all of you. This is the diagram right here. What this basically is an institutional domestic water system. This entire diagram that you see right here is an entire domestic water system, domestic water ecosystem, if you will, okay? It starts over here on this side with the cold water coming into the building. Basically, the cold water travels over to here. We've got a centralized hot water heater right here. Then we've got some centralized master mixing valve going on right here. Also, what we've got is we've got two loops. We've got our kitchen loop and laundry loop, which is 140 degrees, and we've got our faucets, showers, etc., which is 120 degree loop. We've got a circulation pump, we've got some filters, we've got a nanobubble generator. Also, we're going to show you the super saturator nanobubble system as well. So let's get into it. All right, let's talk about a domestic water system in an institutional building. Let's walk through this entire system. Then we'll break it down kind of section by section so you have a little better feel for everything that's going on. We're going to start over here with the cold water entrance. Cold water comes into the building right here. As that cold water comes in, it can split off and go to a mixing valve, and it can also travel through and go on into your building, right? So typically you got one water line that comes in, and then it's got a bunch of branch lines. One branch line feeding your water heater, one branch line feeding your laundry and your kitchen, another branch line feeding domestic faucets and showers and going all over the place, okay? That's the cold water side of the equation, okay? On the hot water side, essentially what we've got is we've got our cold water coming in here, comes down, comes into our hot water heater, right? If we have a centralized water heater is going to heat that water up to 140 degrees, send that out to our kitchen and laundry. So typically we're going to send out 140 degrees to our kitchen and laundry. And then we're also going to send that hot water out at 140 degrees out of the water heater over here to our mixing valve, master mixing station, where we're going to blend in some cold water, and we're going to send that out at 130 or 120 sometimes. And that's going to go over to our showers, faucets, sinks, etc., etc., etc. Okay? Then that's all fine and dandy. We could stop right there. But what happens if the water's not being used? If the water's not being used, no hot water will flow. And so these hot water lines, the 120 line and the 140 line, they're going to get stagnant and they're going to get cold. And it's going to take a long time for these people here to get hot water. Enter circulator pumps, okay? So circulator pump does nothing more than keeps this whole loop moving, keeps all that hot water moving, right? So on the 140 degree loop side, what we have is we have cold water coming in from the street, okay? Comes in the water heater, gets heated up to 140, comes out, goes into the building, goes out, goes through the kitchen, the laundry, all those things like that. Then at the end of the line, it comes back out, comes down, around, and then there's a circulation pump right here. That circulation pump takes the water and it circulates it. It sends it down along here, okay, all the way along here, and then back right up in here into the water heater. So we have a complete loop, right? So it comes back into here, back through here. We have a complete loop. That runs 24 hours a day, 7 days a week. So as that water leaves here and goes out to the building, it gets colder and colder and colder. It comes back, it's a little bit colder, it gets heated up, and that's how we keep that whole loop hot. And then the fixtures, they all just draw off of that line down the road, okay? Now, the hot water also comes out 140 out of the water heater, goes over here into our master mixing valve. We'll talk about why we need a master mixing valve here in a second when we get into that. But out of the master mixing valve, we send out, like I said, 120 or 130. We typically want to make sure that the return coming back is no less than 120 degrees, okay? So let's say we send it out at 130. That water heads out here and it goes over here and it feeds our showers, faucets, etc., things like that. Out of there, we come out here, over here, we come down, and we've got a 120 degree circulator pump right here that circulates that water back along here. But instead of that water going right back to the water heater, where it goes is it goes up into our digital recirculating valve, where it can be redirected. It can either run back out to the system if it's at temperature, or it can go right along here, go back to the heater, where it can pick up a little bit more heat and go back out into the system. And when we get into the master mixing valves, we'll talk about that a little bit more. Now, the other things we've got in this system is a supersaturator nanobubble generator system. What this does is it adds nanobubbles to the cold water side of the building. So all of the cold water coming into the building, which makes the hot water, gets treated with nanobubbles. And we've also got a pair of nanobubble generators, one on our 140 degree recirc return loop and one on our 120 degree recirc return loop. Another thing that you see on here is a couple of different filters, okay? Filters are not required for nanobubble generators, but we do recommend them, and they are actually required for any system that is a demo or a try before you buy or a delayed billing type of a setup. We require that you install a filter so that the customer can observe the scale being removed from their system in real time. And we'll get into exactly what those filters are and what types of filters you want to use. But in essence, this is where the water comes into your building to where it goes out and is used and how it makes a big old circle all the way through it. Let's unpack each of these different areas one by one and look a little bit closer at them. Okay, let's break down our domestic water system, okay? We're going to start with our domestic water entrance, okay? This is where the cold water comes into the building. Basically, it comes in from the street, underground, comes into the building, okay? Typically in the domestic water entrance room, okay, that's where the water comes in. You've got a water meter typically. You might have a backflow preventer, something like that. Sometimes this is in a separate area of the building on a different corner of the building or somewhere else. Sometimes this is in the mechanical room close to your water heater and other equipment. We're showing you this because this is oftentimes where we put a supersaturator system, okay? Sometimes there's enough room in these types of rooms to put a supersaturator system. But essentially, this is where your cold water comes into the building. Now, speaking of cold water, I want to talk a little bit about what's in that cold water, okay? So you got water coming in from the street. In that water, you've got obviously H2O, you've got water, but what else do you have, okay? You've got bacteria. Okay, you might have bacteria, you might not. You've got minerals, okay? If you're in a hard water area, you know, they say you have hard water. Those are minerals, okay? You've got metals possibly. You might have some lead, you might have some zinc, you might have some iron, you might have all kinds of things. The other thing that you have in here that nobody ever really thinks about is oxygen and air and non-condensable gases. And we're going to talk a little bit about those because those are important when it comes to making nanobubble generators. So it's important to know that what's coming in through this pipe right here is not just plain old water that you drink. It's got all kinds of stuff in it. Another thing that it's got in it is chemicals, possibly. Chemicals that the water treatment facility puts in it. Sometimes in the water entrance room, you'll be adding some chemicals like chlorine or monochloramine or different things. So there's all kinds of different chemicals, minerals, metals, oxygen, other types of gases in that water. Some of them are helpful, some of them are not so helpful, and we're going to talk about that and unpack it for you. Next thing we're going to talk about is your water heater, okay? This is kind of the heartbeat of your domestic hot water system, okay? This is depicting a central water heater, okay? Remember we talked about cold water coming in right here. The cold water feeds into the hot water heater. Hot water heater uses some sort of energy to heat that water up to a certain temperature, okay? Typically, we see hot water heaters that heat water up anywhere from 120 degrees all the way up to 220 degrees, like on our digital flows and our flow right temps, okay? The main purpose of that is to make hot water for these users, right? So we're gonna make 140 degree hot water, we're gonna send it out to our kitchen, we're gonna make 140 degree water, we're gonna send it to our digital master mixing valve, and we're gonna send 120 degree water out here for our people to use to wash themselves, okay? Let's talk a little bit about the water heater and why we run it at certain temperatures, okay? Or let's talk about water heaters in general first. Sorry, I'm getting ahead of myself. Water heaters, okay? Water heaters come in different sizes, different shapes, different types. It doesn't really matter. They all do the same thing, okay? They heat water up. They could be a tank type water heater. They could be a shell and tube water heater like this is Armstrong Digital Flow, where it uses steam to make domestic hot water. Could also have something like an electric water heater or a heat pump. And then even you could have point of use water heaters like this. Oftentimes dormitories or apartment houses oftentimes have those. And I'm showing you those because those aren't typically your central water heater right here. They're not usually that style right here. But when you have these types of water heaters, which are oftentimes distributed up here in the building, they just take cold water and they make hot water for individual fixtures. These things will scale up just as bad as this one and just as bad as this one. And that's where the super saturator really comes in handy, because you're treating the cold water, which will really help with these types of heaters. And we've got some case studies to show you on that. Let's talk a little bit now. I didn't get ahead of myself, but here we go. Let's talk a little bit about why do we even heat the water up and what should we heat it up to? I mean, essentially, we only need to heat it up enough to wash ourselves, which is typically between 110 to 120 degrees. Why do we want to heat it up very hot? Well, as you guys know, we want to heat the water up to kill that bacteria. We got that bacteria coming in, and we need to heat that water up hot enough to kill that bacteria. Okay, we recommend, and ASHRAE and ASPE and all the governing bodies recommend that you heat the water up to a minimum of 140. We'd love to see you get up to 158, 160, because up here, you're killing Legionella really fast. The lower you go, the slower you kill Legionella. Okay, the Legionella, the bacteria, you know, we talk a lot about Legionella, but it could be Pseudomonas, it could be any other type of bacteria. The bacteria comes in from the street. The bacteria comes in this line over here, comes into your building. Okay, that's not when it's the problem. Where it becomes the problem is when it's in the building and you get it into these ideal growth temperatures, right? So the optimal growth temperature is between basically 90 and 120 degrees. When that water is at that temperature, that Legionella and that bacteria wants to grow and grow and grow and grow and get really, really big and populated. And that's when you can have a problem, okay? So by generating that hot water, it comes in here, it's pretty cold, right? Typically groundwater or lake water, wherever your source of cold water comes from. Typically it can be anywhere from like 40 degrees out here in Colorado where I live, all the way up to 70, 80, maybe even 90 degrees in the desert climates, okay? That water is going to usually typically be down here below the growth range. So essentially the bacteria is going to stay dormant. It's not going to multiply and replicate. So you have less risk. You don't have no risk, but you have less risk. Again, low risk when the water's colder, getting more risk, more risk, more risk, and then less risk as the water gets hotter, okay? So we're gonna heat that water up to 140 at a minimum, where we know that the bacteria is gonna die within a few minutes. Also, we're recirculating that water as well. Water that's moving has a lot less potential to become proliferated with bacteria and other harmful organisms. You think about a stream flowing or river flowing versus a stagnant lake, it's very easy to see what's going on there. So we've went ahead and we brought that cold water in here with a little bit of bacteria. We cook it right up. We just cook that bacteria, especially with a Digital Flow or our Flow-Right heaters. Man, you put that water up to 200 degrees, it just kills all that bacteria dead, dead, dead. That's awesome. But now we got some smoking hot water coming out of our water heater, which is fine. We'll send it over to our master mixing valve, right? That's going to be able to handle that super hot water and blend it down to a cooler temperature that's easier and safer to deal with throughout the building, right? Because what we want to be careful of is scalding people, right? I can tell you, if you look down here, 140 degree water, it only takes 2 seconds for you to feel that and feel scalded. And it only takes like a few seconds for you to actually get a very severe burn at 140 degrees. So we do not want that 140 degree water coming out here and going into our buildings and our fixtures. That's a bad deal, okay? We want it for killing the bacteria, but we only want it for basically washing laundry and washing dishes, okay? That's because those types of appliances a lot of times require hotter water for disinfecting dishes and helps with cleaning your clothes. But what we want to do is we want to blend that water down to a more manageable temperature. You know, typical showers are between 104 and 110. You know, that's typically what you want to see out in here, okay? So we're going to be blending that water down with our master mixing valve right here, okay? And that's the next thing we're going to talk about is master mixing valves, okay? There's different types of master mixing valves, but their purpose is very simple. Sending out 140 coming in over here, 140 comes into the hot side of the valve, bringing in our cold water over here, okay? Cold plus hot equals warm, okay? And that's how they work. Traditionally, we've had different types of Thermostatic valves have been used for master mixing valves for centuries. Well, maybe not centuries, maybe decades, but they're not the greatest valve in the world for this. They weren't ever designed for this. You can watch Armstrong has whole presentations on why that is. But these valves are what you'll oftentimes see, and that's why I show them to you. Our preference is that obviously you use a digital recirculating valve. This is the Brain by Armstrong's, and this comes in just a single Brain. You can buy it as a flex with a recirc return manifold right here. And I'm kind of getting down in the weeds a little bit, but I think it's important for you to understand these things. So I never miss an opportunity to try and teach you guys these things. The manifold here with the recirc return piping on it, you can get a flex with some valves to help you out a little bit, or get the full meal deal with a digital mixing station, which is really the way to go because you got gauges, you got a bypass, you've got everything you need, strainers just bolted on the wall. Contractor makes it easy to hook up, just a few connections and he's off to the races, okay? The cool thing about these that you don't have with these is that this will manage your temperature, plus or minus 2 degrees, and it will manage this recirculation, okay? One of the biggest Achilles heels of a thermostatic mixing valve right here is that that valve was never designed for recirculation. It was never designed to handle water flowing through it continuously, okay? What it was designed to do was take hot and cold and make warm, okay? So it's not designed for that. Whereas we pioneered the digital recirculating valve that is designed just specifically for that. Okay, and the way that that works essentially is that you got your 140 coming out of your water heater. It's going over here and it's going into the master mixing valve, okay? The master mixing valve is going to proportion and allow in some cold water. This is the cold water side. You can see here's our cold water coming in over here. The cold water is coming in here, and it's going to send out 120 or 100, let's just say 130. The 130 is going to head out here. It's going to go out here to our fixtures and everything. And as it's going along, it's going to lose temperature, lose temperature, lose temperature, lose temperature. It's going to get circulated around. It's going to come back down along here. And then it's going to get right up here and it's going to come in right here. Now, we left the valve at 130, and let's say that we're coming back at 120, okay? What this master mixing valve, this digital recirculating valve does is it decides, okay, I need to add some heat to this water. So what it does is it actually redirects this water. It sends some of this water back up this line, up here, over here, through the water heater, picks up some heat, flows back around, comes back over here. Now the water's getting a little bit warmer. We're starting to get up to close to temperature. Once we're up to temperature, then what it does is it shuts off the flow so it doesn't go through here, and it just allows that water to come through here, okay? So this is both a mixing valve and a diverting valve. It either diverts water back to the water heater or it diverts water to the system, maintaining a plus or minus 2 degree set point, okay? So that's what that does. Next thing we're going to talk about are the recirculation pumps. Remember we talked about the only reason why you need a recirculation pump is to keep that water moving. That's the only thing that it's for. It's not to boost the pressure, to make the building have more pressure or anything like that. If we had a booster pump, it would be over here on the cold water side. I don't show a booster pump, but in a multi-story building, you might have a booster pump boosting this water pressure. But these are circulation pumps, okay? Typically, you might have 1, 2, you might have 20 for all intensive purposes, okay? They could be zoned differently. This is a very simple diagram. But essentially what this does is, like I told you, the cold water comes into the system, goes out of the water heater, take the 140 degree side, 140 comes out, goes out here, goes through the kitchen and laundry, leaves the kitchen and laundry, comes through here. This circulation pump takes the water and flows it along this line right back here and into the water heater, okay? It's really important here that I mentioned that I see this messed up all the time. The 140 degree recirculation pump, okay, right here, when that pipe leaves that pump, that line should go right back to the water entrance going into the water heater, okay? Here's where I see a lot of people, here's a pro tip for you. Here's where I see a lot of people mess up. They pipe this 140 degree water temperature line back over here to the Brain, okay? They stick it in and they pipe it into the recirc return, or they manifold these two together. Here's the 140 recirc, here's the 120. They manifold these two together and they send them both back here, or they send them both back over here. Both of those are wrong and will cause your master mixing valve not to work, and your water temperatures will be wrong. This is the proper way to pipe it. Pipe that 140 right back to the return to heater line. We call this little line right here the return to heater line. On the Digital Mixing Center, you'll recognize that, okay? I'm just kind of showing you if you piped it up in the field, this is what it would look like. On the 120, and let me give you one other tip. An easy way to remember it is the 140 line, whatever line leaves the heater that feeds this pump, it should go back to the same place. So since the 140 just comes out of the heater and feeds the system, that 140 circulator should come right back and go here. Now, the 140 feeds over here, feeds this mixing valve, right? We got 140 degree water coming up here, coming over here, down through here into the mixing valve. Now it comes out of here at 130, goes up here, feeds our fixtures, comes all the way back around here. Here's our circulator. Since that came out of the mixing valve, it should go back into the mixing valve. We don't want that to go back right into the heater, okay? Because it didn't come out of the heater. This water came out of the heater, so it should go back into the heater. This water came out of the mixing valve, so it should go back into the mixing valve, okay? I see more plumbers mess that up in the field, okay? Armstrong's got plenty of diagrams to show you how to do this. But as that water comes back, again, we talked about how it can go different directions, okay? Now, circulator pumps come in different sizes. It's important when it comes to the nanobubble generator, and we're going to talk a little bit about that, okay? They could be just like a little single speed, what I call fraction horsepower circulator pumps. These are not optimal for nanobubble generators. These are typically low flow and low head pressure, okay? You can step it up a little bit and get like a 3-speed circulator pump. These are a little more, typically a little more flexibility when it comes to extra head capacity, but both of these pumps typically run right on their curve, okay? And so when you're evaluating these pumps, you need to look at the inlet and the outlet pressures to try to determine where these are running on their curve. And if you need help with that, you can reach out to me. In modern buildings, what we see more often are these ECM-driven, VFD-driven smart pumps, okay? Grundfos makes one, the Magna 3. You can get an Eco by Bell & Gossett, Taco. Everybody makes them. Armstrong Fluid, not Armstrong Us, Armstrong Fluid. We're the Blue Trap guys. That's the red pump guys. These pumps are smart pumps. They're programmable, or they have all kinds of different settings, things like that. They can be set to run off of a certain curve, off of a certain flow, off of a certain temperature. What I will tell you about these is that they need to just be set to constant flow. Okay, I appreciate that the industry wanted to bring these pumps out and try to save energy, yada, yada, yada. The energy code says that you need to set these pumps back. That's a terrible idea. These circulator pumps should never be turned off. They should never be slowed down. They should never be set back. Okay, because you think about it. If you turn this pump off or slow it down, you start to stagnate this water and stop it from flowing, you're just going to grow bacteria, okay? Water in motion and water at the proper temperature doesn't grow bacteria, okay? Also, it has a lot less opportunity to precipitate scale and things like that. So I prefer constant speed pumps. If I'm specifying a pump, I'm going with a constant speed pump for a domestic water system. These pumps have their place in things like heating water systems and chill water systems where you're looking for variable speed flow to do things like work against loads. As load increases, speed increases, different things like that. But for a domestic water system like this, we just need a little circulator pump to keep that water moving, okay? But one of the things that we're always going to ask that you do also, our brains need constant recirc. So if this pump shuts off, that pump shuts off, we have no more flow through our recirculation valve, and that's not going to be good because that valve's going to hunt all over the place. So when you're setting up a nanobubble generator or when you're setting up a brain, another pro tip for you, you want to make sure that you program this pump or that pump to constant flow. And every pump has a little bit different setup of how you do that. If you need help with that, please reach out and I can help you with that. Next thing we're going to talk about is nanobubble generators, places you can put them, okay? You can do a supersaturator setup, and we'll get into what this is, but basically a nanobubble generator for your cold water coming into your building, or you can put nanobubble generators, and this is an and or, okay? You can put nanobubble generators, one is enough, but you can also add multiples in different parts of the building, depending on if you have a huge building with a lot of pipe, depending on if you have really hard water and you feel like you need additional ones. One will do the trick and it'll put nanobubbles in your system. So the other places you can put them are on the 140 degree recirc loop or on the 120 degree recirc loop. Where and when you would put nanobubble generators there, we're still learning and we're still applying it. Our most typical application that we have to date is on the 120-degree recirc return loop. We've had very good success with that, descaling the entire system. We've also put them on the kitchen loop, and we've also done the supersaturator and had equally good luck. So it's more of a, what does the customer want? What does the ease of installation look like? The only caveat I will say is if you have point of use water heaters, you don't have a centralized water heater system, or you don't have recirculation return, or maybe you have a faulty recirculation return system, okay? This type of setup over here relies on this recirculating system working, okay? And oftentimes in these buildings, folks, these pumps are often not serviced well, they don't run well, maybe they don't run at all. People, if this pump doesn't run, these people don't have hot water very often, but sometimes they don't complain, okay? More often, I've been a plumber 35 years, and I've walked into plenty of buildings where that pump wasn't doing anything and nobody was complaining or anything else. I want to keep you guys out of trouble, okay? If that pump is not flowing and you add a nanobubble generator without checking to see if that pump is flowing, you will not make any nanobubbles, because no water through the nanobubble generator, no flow means no nanobubbles, means no scale removal, means an unhappy customer. So we always want you, pro tip, we always want you guys to be checking the flow rate of these pumps, okay? What I would recommend when you're sizing up these nanobubble generators and when you're applying them is that you put a strap-on ultrasonic flow meter. Armstrong Verus makes one. I use it. I bring it out and strap it right on the pipe. Strap it right on that pipe and see what that flow rate is, because you can take that flow rate, whatever that's running, check your differential pressure on the suction and the discharge side of your pump. Look at the pump curve that you can download by looking at the pump data tag. See who makes the pump. Pull up the data sheet, the pump curve on it right there. Look at where the flow rate is and the pressure drops, and you can see exactly how much appreciable head you have left in that pump, and you can see if it's actually flowing. Also, make sure that that pump is not set to turn off. Make sure it doesn't have an aquastat on it. Make sure it's not on the BAS system where they say, oh yeah, at night we turn that pump off, okay? I see those types of things, because trying to keep you out of trouble. Just because that pump turns off and nobody complains, it might not be any big deal. But if that pump turns off and it's not flowing, we don't have any nanobubbles being made, so we deplete all of our nanobubbles. We don't have any descaling. Our master mixing valve is going to hunt all over the place because it wants to see continuous recirculation. So this is really the heartbeat of the circulation system, and you need to be very careful with making sure that that pump is in serviceable condition and that it has ample head pressure to push the nanobubble generator. And we're going to get into exactly what I'm talking about when it comes to those types of things. Okay. Last thing I want to talk about here are filters. I've got a set of filters drawn on here. Okay, right over here around this pump. This is our preferred way of piping filters. Okay, I'm going to show you what kind of filters we would recommend. There's two types of filters that we would recommend that you guys use on these systems. First one is shown here is a cartridge filter. That's this little guy right here, sometimes called a whole house filter or something like that. The other type that we would recommend is a bag filter. Okay, this is a commercial bag filter. You're going to want a stainless steel bag filter because this is domestic water. We do not want an iron body or a steel bodied filter housing. You're going to want stainless steel. And the way that these work is essentially there's an inlet and an outlet, and then basically the top comes off. You take the top off and you pull out a bag or a sock, which is basically the filter media, and you can inspect it and clean it and change it. And at the end of this presentation, we're going to show you some of those filters, what they look like once you add the nanobubble generator. On a cartridge filter, my preference would be that you use a clear acrylic cartridge where you can see it, okay? And this is one of the photos that we have. This is not my preferred method for installation. We're going to talk about why. This is our preferred method. But essentially the way that this one here works is that the water flows this way, comes through here. You've got a bypass valve that's closed, so all the water is forced through the filter, goes over here, down, and comes through our nanobubble generator. Down here's our nanobubble generator, and then it goes back to our water heater. We've got a semi-instantaneous vertical water heater over here. Okay, why I don't like this setup is because as a filter gets plugged, okay, water's going in here, as this media gets plugged, it ends up creating a significant pressure drop, almost to the point where it could stop flow. So we need this line flowing all the time. We don't want anything to stop that from flowing. If they don't monitor this filter and keep it cleaned out, when it gets plugged, we're going to stall the nanobubble generator, we're going to stall the recirc pump, we're going to stall the recirc return, and we're going to cause our brain to hunt all over the place, and it's just going to be a lot of problems for you. So this is our preferred setup, okay? Remember, this is our line coming back from our kitchen, our 140 line, okay? Comes over here. Here's our pump right here. What you're going to do is you're going to take a branch line off of your pump, go to the inlet side of your filter, come out of your filter, and go right back into the suction side of the filter. The way you're going to size this is you're going to size this for 10% of the flow rate. So whatever this line is flowing at, say it was 10 GPM, you're going to size that for 1 GPM, okay? That makes it very small, very compact, very easy. All you're doing is basically diverting a little bit of water through the filter and back into the suction side. And over time, that's going to clean up the system, okay? Also, why I prefer this is because as this filter gets plugged, it's not going to deadhead this pump. It's not going to cause any appreciable problems with deadheading this pump. Whereas in this scenario right here, you have the potential to deadhead your pump. In this scenario here, you don't, okay? These types of filters, the bag filters I was telling you about, these are pretty slick because they typically come with differential pressure gauges, either ports on the filter housing for gauges, or for sure add differential pressure gauges. And also these bag filters typically come in different micron ratings. And what I would suggest is that you start at 100 microns, okay? And also the good thing about filters, bag filters in particular, but cartridge filters as well, is that as a filter gets plugged or as sediment and things get built up in it, it actually filters better than it started, okay? And so don't start with a super fine like a 10 micron, okay? Because that's gonna just plug up really fast. What you want to do is start with a higher micron, meaning bigger openings, and kind of start there, get the bigger gunk out of the system first. Then as you see it starting to last longer, it's not plugging up as fast. And again, by having inlet and outlet pressure gauges, you'll be able to tell what the differential pressure is. So most filter manufacturers who they publish what the flow rate, the pressure drop is for the filter when it's new. So when you put a brand new filter and it's completely clean in there, what it'll say is, for instance, the differential pressure should be 2 PSI. So what that means is that if this was coming in at 50, it would be going out at 48. Then what they'll say is for this particular sock or filter, when you have a 10-pound differential, that filter is essentially completely plugged and it needs to be replaced. Okay, so that just means you look at those two gauges. When you have a 10-pound differential, you know you need to replace the filter with a new filter. The other cool thing about this setup is you basically just close these two valves. You can open up the top, pop it out, look at it, inspect it, things like that. One thing I want to remind you of is that when we do a delayed billing or a trial installation or something like that, you must install one of these two types of filters in the system, okay? This is the easiest place for us to observe the scale removal is right at the filter, because we can pull those out, we can examine them, take pictures of them, and that's a way to show the customer that they are removing scale, okay? Now, let's talk a little bit about these filters and how they work in the system, okay? And how to set these up for a delayed billing setup, okay? I wanna really kind of walk you through that really quick. What we want to do on a delayed billing setup is the first thing we want to do is we want to get this filter installed. Go ahead and install the nanobubble generator if it's here, or even if it's over here, if it's a super saturator or a hot water return, doesn't matter. Install all of that, install your filter. Don't start your nanobubble generator up. Leave it off, leave your bypass valve wide open so there's no water going through the nanobubble generator. Go ahead and start your filter up, okay, which essentially just means opening this valve, opening that valve, and let that filter run for a week. Just let it run, just let it run, let it run. Let it fill up with sediment. Let the customer see what just water flowing through that filter looks like, and keep it going until you get a clean filter, okay? That way you know you've removed most of the sediment, because when you've cut the nanobubble generator into an existing system and you do all this work, you're gonna break loose a lot of scale and stuff, and it's gonna find its way to that filter. Because what you wanna do is you wanna show the customer that before nanobubble generators, we had a clean filter, okay? If you start both of these up at the same time, nanobubble generator plus the filter, the customer could say, well, I don't know, was it nanobubbles or was it just the water flowing through there, okay? So let's just start this up with no nanobubble generator engaged, run it just with the cartridge filter or the bag filter, collect scale over a week or 2 weeks, just run it until it runs clean, until you put a clean filter media in. Once you're not getting any more sediment in the filter, appreciable sediment, especially big sediment, Once it seems like it's staying pretty clean, then what you can do is go ahead and fire up the nanobubble generator. And we'll talk a little bit about how you do that. And I have a separate video specifically on how you start these nanobubble generators up and balance them on the recirc return line. Okay? Okay, let's talk about what's in my water. So we're going to talk about a few things that you may not be aware of. Remember we talked about when the water comes in the building? Okay? A couple things to talk about here. There's non-condensable air and gas found in tap water. Okay? You've got nitrogen, argon, oxygen, okay? N2O2, CO2, okay? You got non-condensable gases. This is what we make nanobubbles with, okay? It's important for you to understand tap water coming in from the street has all of these gases in it, okay? And this is what's important for making nanobubbles. What else do you have in your water? You've got things like bacteria, Legionella, Pseudomonas, Mycobacterium, things like that. Maybe, maybe not. Not every system has bacteria in it, okay? But if you do have it, these are the typical kinds that you have. The big poster child everybody knows about is Legionella, causes Legionnaire's disease, but there's other ones like Pseudomonas, NTM, things like that. You may or may not have this in your system. It's primarily a main concern in hospitals and in healthcare centers and things like that. Another thing we have in here is minerals and metals, okay? And the minerals right here, calcium and magnesium, those are the main things that we want to talk about when it comes to nanobubble generators, okay? Because that's the primary purpose of even installing a nanobubble generator, is when you have water that's high in calcium, high in magnesium, okay? Other things you might have in your water are iron, manganese, copper, zinc. What's important for you to know about these minerals is that they're naturally occurring in the groundwater, okay? They're dissolved in the water as they comes in the building, okay? The other thing that I want you to remember about them is that they're ionically charged +2. So if you look at a chemistry chart from high school, you'll see that they have a ionic charge of +2. And that's going to be important when we talk about nanobubbles, because nanobubbles are negatively charged and minerals are positively charged, and positive and negative join together. And that's the whole action of how nanobubbles work on removing and inhibiting these types of minerals, okay? The other thing that people don't think about, but oftentimes occurs, is you've got other things. You've got chlorine, chloramines, maybe some ozone, maybe some phosphate. Primary disinfection, say from the water treatment plant, they might be adding some chlorine dioxide. They might be using ozone, different things. They might be adding some fluoride and some different things. These are to kill the bugs in the water. These things down here are, fluoride is for your teeth and things like that. And then at the bottom down there, the supplementary type of things are things that hospitals and other customers who end up having bacteria problems in their buildings, they'll add a supplementary system, such as a copper-silver ionization system, or a system that injects chlorine or monochlorine, doses it into the water. And it's important for you to know that, because these things are powerful oxidants, and they're really good at killing bacteria, but they're also really good at eating up metal pipes and eating up and corroding metal and causing all kinds of damage to stainless steel, which is in your heat exchangers for your water heaters, and coppers and brasses and zincs in your valves and things like that. So these are great for what they were intended to do, but they tend to tear up plumbing systems, especially when they're overdosed and they're put in at too significant of a dose and they're not managed, okay? So let's talk a little bit about, all right, we saw all those things. What happens when those things get into this ecosystem, right? You got all this water moving around in this system, and it's got those minerals, it's got that bacteria, it's got that air, it's got that nitrogen, it's got some chlorine, it's got all kinds of stuff in it. And then all of a sudden we're heating that water up, we're making it go fast, we're making it go slow. What actually happens, okay? Well, what happens is we get stuff like this. We get buildup, we get all kinds of corrosion and sediment and scaling of heat exchangers. That's a shell and tube heat exchanger with a lot of buildup on it. We get other things like mineral scale precipitating out on this electric water heater element. So essentially you can see this white stuff right here is lime scale buildup on a water heater element. And when you have something like that happen, what do you think happens? The heat that's on that element can no longer heat that water up, because that scale is an insulator. That's the biggest problem with scale, is as it precipitates out and sticks to these surfaces, when it comes to heaters like that one, like this one here, all that buildup in there just creates an insulator between the heating surface, whether it be steam or electricity in this case, and the water. And so now that water heater is working a lot harder to make the same amount of hot water, and it's wasting a ton of extra energy, right? From an unsightly standpoint, like in hotels and whatnot, here you see a shower head. What you got going here is when you turn the shower off, you have a little bit of water there that kind of sits there on the shower head. That water evaporates off, right? And basically it leaves behind a little bit of limescale, okay? Get the same thing on your faucets right here, okay? And this is especially bad in a hospital because basically if you have scale buildup like this, that's a great place for bacteria to hide in there as well. The good news is nanobubbles is going to help with all of these things, okay? Other things that we see, and trust me, my phone is full of these kind of pictures, and I'm sure yours probably is too, but what you're looking at there is a Y strainer basket, and it's got some sort of buildup, probably biologic buildup, as well as some scale buildup, goopy stuff, right? Here's a nice looking check valve, right? A big old iron-bodied check valve. Unfortunately, I see a lot of iron-bodied check valves in domestic water systems with rapid oxidation, okay? So you've got iron oxide going on here, which is a combination of corrosion of the iron and oxidation from the minerals. So remember, water can be corrosive and it can be scale forming, both at the same time. You can have one by itself, or you can have the other by itself, or you can have both. In this case, you're looking at some of both, okay? Same thing here. That's not strep throat. That's actually looking down into a check valve. You can kind of see the check down here in the back, but you can see the buildup here. You've got some kind of possibly iron oxide, possibly some sort of bacteria, and some limescale built up, okay? And it does look like you might have strep throat back there. Here we go. This is a strainer on a inlet to a domestic water circulator pump that's all filled up with scale and packed in tight, right? So a strainer basket like this is not going to flow very much water. In this case, when we took this strainer basket out, the pump wasn't able to flow any water at all. Again, we're talking about these circulator pumps right here. That strainer basket came out of this strainer right here, okay? Now, I want to just give you another pro tip right here. Blowing down strainers does not remove this type of scale, right? So if you've got a blow down valve, you can kind of see it here, the blow down valve. Just opening that valve up, even if you open it wide open, first of all, you can't get much water to even flow across that strainer because that scale is so hard packed. So when you open that valve up, especially if you see only a little bit of trickle of water come out, you know, you should have about 40 pounds or better on this system, right? 40 pounds coming out of a garden hose is a pretty good stream. It should jump out of the drain. You should have to keep your foot on it. So if it's just kind of petering out a little bit, chances are you got something like that. But either way, go ahead and remove that basket, remove that bonnet, pull this screen out, and actually clean all of this out because this is bad news, okay? Next thing I want to show you is on the downstream side. So we have a check valve. Right over here is a check valve, okay? That's on the downstream side of the pump. And you can kind of see down inside of here. Here's the check valve right here. Here's the check disc right here. Okay, this is a swing check. And you can see buildup of scale. And you can see that scale's kind of got some bacteria on it, some biofilm maybe, different things. That was effectively scaled shut. At the point where that's right there, I had actually banged it on the floor and made the flapper kind of start working. But before, when I first took that check valve out, it was actually scaled shut. So essentially the flapper had lifted up, had stuck there, and it had scaled all up, and the scale bridged between the flapper and the body, and there was no water flowing through there, okay? If you have these two types of conditions, if you've got a plugged inlet strainer, okay, so if this strainer on the inlet side of the pump is plugged, a lot of times the condition that you will see is that you'll have very low suction side pressure. That's why it's important to put gauges on the suction and the discharge of a pump. Even if it's a small pump, gauges are cheap. Put a gauge on the suction and the discharge, okay? You'll have low suction pressure because think about it. Water can't really get through there. You know, even if it's high pressure over here, especially, you know, since this is going to be basically street pressure, okay, street pressure pushing on here, okay, but if it can't get through there, it's going to be low pressure. And that's exactly what this customer had. Because this was plugged up, he had very low suction side pressure. At the same time, he had a plugged up check valve, okay? So this check valve over here was completely plugged and clogged. So this pump was pumping like heck against a shut check valve, a stuck check valve, which is essentially like a shutoff valve. So the head pressure on the pump was real high. So with that pump, for instance, we had a suction of like a couple PSI and a discharge of like 20 or 30 or 50 PSI. Anytime you see a huge discrepancy, especially when you look at the pump curve and you see where the pump should be running at, when you see a huge discrepancy, you should be suspecting things like plug check valves and clogged strainers. Okay, that's it on the pro tips on those two. Okay. Here's another thing that we like to look at is these pipes. So all these pipes throughout this system, right, especially the hot water pipes. So these cold water pipes, remember our cold water's coming in, it's probably between 50 and maybe 90, like 90 would be on the high side. Most domestic water coming in the greater United States is going to be between 40 and 60, 70, maybe 80 degrees. But also when it comes in the building, it's coming out of the ground at 40 degrees or 50 degrees. But as it gets in the building is heated up to ambient temperature. Maybe it's 70 degrees in the building. Maybe these pipes are running next to steam lines. Maybe they're not insulated. It's an old building. So those cold water lines can actually start to get up in temperature. And as they start to increase in temperature, they will drop out scale. Okay, so the cold water lines will drop out scale. The hot water lines will drop out scale much, much faster because the faster you heat the water up, the faster the minerals try to escape from the solution and stick to the pipe. But you can have scaling in both the hot and the cold. You can also have bacteria in both the hot and the cold. And as that scale builds up, it sticks to the pipe really, really bad like that. Okay, let's talk a little bit about how mineral scale forms. So we mentioned that the minerals are coming in out of the groundwater. You've got calcium and magnesium. Those are the two primary minerals that cause limescale. They're in solution, right? So they're just floating around in the water, no problem at all, okay? And they just float in here, again, as the water starts to change temperatures, as it starts to go from high pressure zones to low pressure zones, as it starts to go faster and it starts to go slower, and especially as it starts to heat up, whether it's just gaining heat from ambient or it's going through the water heater and getting heated. So it's getting heated up, and then it's going over here through the mixing valve and cooling down and then getting heated back up. And it's heading out into the system where maybe some of these branch legs, you got a branch line that comes over here. It sits for a while and it starts to get a little bit colder. All that change in heating and cooling of the water causes those minerals to go through this little process over here. And I'm going to walk you through this clustering, nucleation. It's not super important that you understand it, but what's important for you to understand is that the minerals go through a change and they leave the solution, okay? So what you've got is the clustering, which is the dissolved calcium and carbonate ions begin to group together in the supersaturated water. Then you have nucleation, which is small, stable seed crystals that form these little clusters. That's kind of the starting point of the limescale. Then you have crystal growth, which crystals attract more ions. They grow larger as the mineral concentration stays high. Then you have flocculation, which is individual crystals collide and stick together, forming larger aggregates, okay? Then we actually get into what we know as traditional scaling. These crystals then attach to the metal pipe, the heat exchanger surfaces of your water heaters, your mixing valves, different things like that, forming, they stick right onto the boundary layer, creating the hard limescale deposit. The boundary layer effect is a low flow stagnant area which promotes the adhesion, growth, and thickening of the deposits. And on this diagram right here, what you're looking at is that boundary layer is right here, this little red layer between where the scale is and where the pipe wall is. What you have going on there is both a low flow area where the adhesion of the scale starts, and you also have corrosion going on there. But that's essentially what happens. And then just over time, that scale just builds out, and out. And you can imagine, as you build up more scale like this, you're increasing velocity because you're reducing the size of the pipe, which is going to increase the flow, the velocity through there. It's also going to reduce the flow rate, and it's going to cause pressure drops, and it's going to cause all kinds of problems within your pipe. Within your heat exchangers, like your water heaters and things like that, anything like this where, for instance, if you have steam on this side, if this was a tube and you had steam over here trying to heat that water up and the water's down in here, this is just an insulator, okay? This is just insulating it. And it takes a lot of steam to make that heat go all the way down here to that water, okay? So this is an insulator, so it causes reduction in heating capacity for your domestic water heaters, and it causes flow issues and all kinds of problems, as well as it grows bacteria and other things on it. So some common forming mineral scale minerals, we talked about them, but as they scale out, this is what they're known as: calcium carbonate, magnesium carbonate, calcium sulfate, calcium silicate, iron carbonate, calcium phosphate, and silica. And I'll show you kind of a little bit with what these kind of look like. So here's our traditional calcium carbonate. This is pretty much the typical lime scale, if you will, that we see in pipes. It's typically white, crystalline, excuse me, chalky type of deposits. The next one is magnesium. So magnesium typically plates out more of a light gray, and it's a lot more powdery, okay? And we can do water samples to determine if you have calcium or you have magnesium in your water. Good news is nanobubbles will work on either one of those. Calcium sulfite looks a little bit more squirrely. It kind of has these like strands. It almost looks like insulation, if you will, or it just has kind of that striations. Then you've got your calcium silicate. Kind of looks like that. If you have like little pellets, they actually form these little pellets. They look a little bit like that. Iron carbonate, I showed you that already, or iron oxide sometimes I call it. But essentially what you've got going here is a combination of corrosion and bringing iron in, or you may have iron in your water and you have that iron precipitating. So this is iron in the water that's precipitating, but also you can have iron that corrodes off of a ferrous metal within your system that gets into the water that then also precipitates out as well. Then we have calcium phosphate. It's looks a little more like that. And then silica. So if you have silica in your water, you can see here's a shell and tube heat exchanger with silica deposits on it. They're kind of clear, glassy, typically very hard, glassy types of deposits. Now let's talk a little bit about bacteria and scale, okay? So oftentimes bacteria and scale co-occur. We talked a little bit about that in the Legionella section, but it's important that you understand that when you have a scale layer build up, okay, that's the ideal breeding grounds for bacteria. So as bacteria moves into the water, it comes in contact with that scale, and then what it does is it knits itself into that scale. So that bacteria goes out of the water, it sticks to the scale, which is porous. Even the real dense scale is porous on a microscopic level. It sticks in there and it kind of weaves its way into that dense scale layer, and it makes a nice home. It's really resilient. You know, even though that water's jetting by there, it kind of weaves itself up into that scale so it can stay there and grow. It also feeds off of that scale, and that's what causes this biofilm layer. That's what causes this biofilm layer, okay? So you got scale buildup right here, and then you got biofilm, okay? You could have biofilm buildup on a pipe wall, but it's far more common to have biofilm buildup on a scale layer, okay? So the cool thing is when we remove the scale layer with nanobubbles, the biofilm layer goes right with it, okay? All right, nanobubbles to the rescue. Let's talk a little bit about nanobubbles, okay? What are some of the properties of nanobubbles? Nanobubbles are nanoscopic air bubbles, typically between 50 and 200 nanometers in size. They have very strong, stable surface tension, a lot of energy inside of them. They're microscopic or nanoscopic, constantly in motion. We're going to talk about that. Negatively charged. Remember, we talked about the minerals being positively charged, the nanobubble being negatively charged. Negatives and positives, they want to get together. That's very important. And they're made from the existing non-condensable gas. Remember, we talked about what's coming in our water? And we've got those airs, they've got oxygen, carbon dioxide, nitrogen coming into our water. Okay, this is what they look like in solution. If we were to blow it up, if we were to look at them under a really high-powered microscope, we would see that they constantly move around. They don't rise up to the top and pop like traditional air bubbles. You can kind of see here's a traditional air bubble, a large macro bubble. It's going to rise to the top and not be very useful. What you're looking at here are two vials of the same water, okay? What you've got here is just regular tap water, which has a lot of entrained air, oxygen, nitrogen, carbon dioxide, and all those types of things, and some nanoscopic bubbles. You can see where this laser is shining through here. And then what we did was we took this water and we processed it through a nanobubble generator, and this is what comes out the other side. You can see all those larger, middle-sized bubbles are all gone. They've all been shredded and cavitated into nanoscopic bubbles, which is why you see this tight laser beam coming through here. That's nanoscopic bubbles, and we'll talk a little bit more about that. So how does the nanobubble generator work? Okay, let's talk a little bit about how a nanobubble generator works. The way a nanobubble generator works is pretty simple. Essentially, you've got those non-condensable gases. You've got oxygen, nitrogen, carbon dioxide, okay? And they're pretty good size. They're bigger size bubbles. They're not nanoscopic yet. As they travel through here in the water, they go through these high pressure zones and these low pressure zones. So this cutaway is showing you one of the pressure zones, but throughout this longitudinal section of this nanobubble generator, there's multiple sections that have different size holes and different size orifices. And essentially what we're doing is we're cavitating and we're shearing that air, okay? We're changing the physical properties of the water. And that's all we're doing is we're shredding those bubbles and making them smaller and smaller with every single pass. These nanobubble generators, as water flows through them, it goes from higher pressure to lower pressure. And here's showing you a little flow chart. For instance, on our 3/4 inch, basically at 1 gallon per minute, you've got a 2.5 pound pressure drop. That means the water comes in here, say it was at 10 pounds, it would come out here 2.5 pounds lower pressure. And we'll talk more about that as we kind of deep dive into what a nanobubble generator is and how it works. This is the basic setup on how a nanobubble generator is piped. This is what we traditionally call the side stream piping, okay? So for your domestic hot water recirc return lines, this is how you would pipe them up. This is also how you pipe them up on a supersaturator minus the bypass, okay? And we'll get into unpacking the supersaturator here in a second. But what I want you to realize is that the heartbeat of this system is your circulator pump, okay? That circulator pump has got to move that water all the way through this nanobubble generator so that it can shred and cavitate that air and make those nanobubbles. So it's super important that this pump has enough head pressure to be able to push water through this nanobubble generator. Our nanobubble generators from Armstrong create a 5 pound pressure drop. The minimum is a 5 pound pressure drop. Remember we were looking over here? So at the optimal flow rate, you're looking at a 5 PSI pressure drop. So this chart is just showing one nanobubble generator. In the IOM, there's a full chart showing all the sizes from 3/4 inch up to 6 inch, and they all look the same. They have a flow rate in gallons per minute and the corresponding pressure drop, meaning that essentially when water flows in one side, you have a certain pressure, in our case, 60 pounds of pressure. At the proper flow rate coming out the other side, it'll be 5 pounds less, 55 pounds of pressure drop, okay? So that's the work that we're expecting this pump right here to do. And you remember we talked about pumps, and so it's super important that you check that this pump can handle the extra head pressure that this nanobubble generator is going to add. So the way we pipe these is we're coming along here, we add a balancing valve. This could be a circuit setter, a globe valve, doesn't really matter. We do that so that we can pinch this down a little bit, which is going to force water to come up through this line here. We add a Y strainer right here with a blowdown valve, and you can put an automated blowdown on that as well. We'll talk about that here in a minute. And then we have a pressure gauge, an inlet pressure gauge, nanobubble generator, and an outlet pressure gauge. You can also use a differential pressure gauge in lieu of 2 individual gauges. Sometimes it's a little bit difficult to see a 5 pound pressure differential, say between 2 0 to 100 pound junk gauges, I call them, small supply house gauges that cost $10 or something. Oftentimes those gauges are 5 pounds off in calibration. So for instance, on our packages, we sell this as a complete package where it's all pre-piped with the strainer and the circuit setter and everything. We use a differential pressure gauge. Makes it really easy to dial these in. So I always recommend a differential pressure gauge. But you're going to set this thing once, because this pump is going to run continuously. Very, very important that that pump runs continuously at the same flow rate. We don't want that pump going up and down and being different types of variable speeds, okay? We want it running at a certain flow rate, okay? That's going to flow water through here. We're going to have a 5 pound pressure drop created by this valve right here, which is going to flow a certain amount of the water up through here. And then we're going to have a 5 pound pressure drop across a nanobubble generator. Then those 2 streams join in and head on down the line. That's the basics of a side stream setup and how we would ask that you always pipe a nanobubble generator. Then, like we mentioned, that water's coming through here. It's got those non-condensable gases. Some of it goes in here that gets shredded and cavitated. Out comes the other side, comes the nanobubbles, goes out to the system, comes all the way back around, does it again. That's why we want constant recirculation, have this water constantly moving throughout this system so that it's constantly going in and out of the nanobubble generator. Okay, let's talk about the nanobubbles in your water in your pipe system, okay? One thing I want to point out to you guys is that nanobubbles change the physical properties of water, not the chemical properties, okay? So unlike traditional water treatment like adding chlorine or adding an acid or something like that that actually changes the water chemistry, what we're actually doing is causing physical changes to the air that's inside of the water. We're not actually changing anything that has anything to do with the water, okay? Here's a little pro tip for you. I've had people ask me, do nanobubble generators split the hydrogen and oxygen molecule? So, you know, water is 2 parts hydrogen, 1 part oxygen. I've had people call me and say, well, does the nanobubble generator split off that oxygen? No, it does not. The nanobubble generator actually just works with the existing non-condensable gases, the air that we talked about earlier, in your water system, okay? So now let's talk about what we got going here, because here's a pipe with water flowing through it, nanobubbles flowing through it, and what you're looking at up here is a layer of scale built up. And as you can see, the nanobubbles are coming in contact with that scale as they're flowing through. And what's going on inside of there? Okay, let's talk about that. How do nanobubbles remove limescale? Okay, so you've got this deposit right here. I'm gonna move back for a little bit. You've got this deposit right here of scale. What actually happens is as these little tiny microscopic nanobubbles come in contact with that scale, when the nanobubble bursts, there's a little tiny microcavitation there, a little micro explosion that breaks a little tiny piece of the scale loose. And if you think about it, this little nanobubble is less than 200 nanometers in size, right? So very, very, very tiny. These little pieces here are even tinier. So this is happening at a sub-micron level, okay? Very, very tiny. When I say a little microcavitation, don't freak out. That's not some sort of a cavitation that's going to cause pitting or impeller problems or things like that. It's basically just softening up the scale and bringing it back into solution. The process takes quite a while. So you can see down here, these are results from an actual customer where they installed the nanobubble generator and they had about that much scale build up on their pipes. Just after 1 month of running these nanobubbles through their system, now all of a sudden they're down to that much. After 8 months, they're down to even less. So over time, those nanobubbles will soften up and loosen up those deposits, bring them into solution where they naturally travel down the pipe stream and are flushed out naturally through the faucets and through the showers and things like that. In the beginning, you can actually have kind of a looser knit layer here where the scale is looser knit. That may come out sooner and faster and be of larger size. And we'll show you a few pictures of some actual results here at the end of this presentation. So that's how nanobubbles remove scale. Now let's talk about how nanobubbles could remove biofilm, okay? Because that's another thing people ask about is biofilm. So again, here's our pipe. This little layer here is our scale layer. Now what we're showing is a little layer of biofilm, right? So what happens inside the pipe is as scale builds up, if there's any type of bacteria in this water, what it wants to do is go up into this scale, and that scale is porous. And what it does is it builds a little scaffolding. The bacteria will knit themselves up into that scale and embed themselves. And they find a nice little home there where there's a good, perfect temperature in there. And also they're outside of the violent stream of water. So you got water going through here. It's pretty fast. It can get, the bacteria can hide up in here. Also, if you put chemicals and things like chlorine and stuff in here, it's harder for them to get up into this scale where that bacteria knits itself up in there. And it makes a nice little home, which is called biofilm. You may have heard that term, right? So if you look at this little diagram, you've got the outside of our pipe, you've got your scale layer, then you've got your biofilm layer. Okay. The good news is that nanobubbles will help with this as well, because what happens is as that water flows through here, those nanobubbles will come in contact with that biologics. They'll explode, release a natural antibacterial agent. It's called a free radical, a little bit of energy to kind of help break up some of that biofilm. But what's more important is that while this image right here shows it looking very uniform, when you look down inside of a pipe, and we're going to show some images, it's usually very jagged where you have kind of clumps of biofilm and then clumps of scale. what really happens to help remove that biofilm is that we remove this scale layer. So as those nanobubbles get this scale layer out and they take the scale layer out, that bacteria and biofilm comes right with it and cleans everything out. So get rid of the scale, you get rid of the biofilm, and you get rid of the bacteria. So that's how we can help with biofilm. We do not sell the nanobubbles as a direct removal of biofilm. We're still studying that and trying to understand it. But we do know that when biofilm occurs with bacteria and we remove that, when biofilm occurs with scale, when we remove that scale, we remove the bacteria as well. And we have proven that with scientific results that we're happy to share with you. Now, let's talk about how nanobubbles can inhibit scale and biofilm buildup, right? So kind of what we're looking at here is, let's just say this was a brand new system. Pipe is brand new. There's no scale buildup yet, okay? But we do have scale forming minerals in the water. Again, if we have hard water, we have calcium and magnesium floating around as minerals in the water, okay? That's kind of what this is showing down here. Remember what I told you, that these nanobubbles are negatively charged on their surface. So the outside of the bubble, this part out here, the surface of the bubble, is negatively charged. In solution, calcium, magnesium, these minerals are positively charged. So as those minerals are kind of floating down through here, in the water, what they want to do is they want to naturally bond together with the nanobubble, and they form what we call microcrystals, okay? So essentially what you've got is a nanobubble with these little pieces of with these little pieces of minerals, being calcium, magnesium, also manganese, iron, any of those +2 or anything on the positive side of the ionic charge on the chemistry chart that we've talked about, are going to naturally bond with those nanobubbles in solution. And again, we've got billions of nanobubbles, so there's lots of opportunities to make these little nanocrystals, right? Once you make these little nanocrystals, they're much less likely to precipitate out. They just keep flowing, right? So the minerals themselves, like if these little dots here were the minerals, those would, as they kind of go through the heat exchanger and things like that, as we talked about before, those would want to precipitate out and form limescale on the heat exchanger. What we've come to realize is that when you make these nanocrystals like that, they tend to just flow right through the heat exchanger and right out the drain, and they don't precipitate out. The net effect is that we actually inhibit scale buildup in heat exchangers, in the pipes, and things like that. So for a clean system, we still recommend nanobubbles, because putting them into a clean system means, or a new system where you don't have scale buildup, means that you'll bond with those minerals and keep them from precipitating out, okay? Also, as we clean the system, once we have a clean system, the net effect is that the minerals don't precipitate back out longer term, and we keep the system clean, we keep the equipment running more efficiently, and we don't have that scale buildup. Also on your shower heads and things like that, when that water that has nanobubbles and those minerals are bound in these crystals, when that water evaporates, it doesn't deposit those minerals, because these crystals are in a different composition than the native minerals of calcium and magnesium that do want to plate out. So for customers that we have, for instance, in the hospitality industry, who have installed these, who have had those problems where, for instance, a shower head may build up that white, chalky, difficult to remove deposits where they have to use some sort of cleaning agent to really scrub that off. After installing a nanobubble generator and running nanobubble water, those exact same showers now don't have that hard deposit built up on them. If there's any type of deposit there, it's easily wiped off by the cleaning people, and there's no additional scrubbing or actually removal and cleaning or removal and replacement of those. So that's the way that nanobubbles inhibit scale. And also when it comes to biofilm, right? If we don't deposit a layer of scale on here, we don't create a home. So that's going to reduce the risk of building that biofilm in your system. Okay, let's jump into nanobubble generator installations, okay? Where would you install a nanobubble generator in a domestic water system, right? Go ahead and pull your diagram out here. We've already walked through what all these system components are. Now let's talk specifically about how we apply nanobubble generators to our system. The first system we're going to talk about is the supersaturator system. Again, this is designed for the cold water inlet. The other two systems we're going to talk about are the domestic hot water recirc return on the 120 degree side and also the domestic hot water return on the 140 degree. We'll just talk about one of them because essentially the piping on them is the same, okay? So let's start first of all with our supersaturator, right? This is the cold water supersaturator with the nanobubble generator. Again, this is going on the cold water entrance coming into the building. So the cold water comes into the building, right? It's going to come up over here and our supersaturator system is going to be all these components right here. Couple things to keep in mind with this system. It relies on the fresh, cold water, non-condensable gases, which all of our systems do. The non-condensable gases coming in from the street that naturally occur in tap water. Okay, it's going to take that non-condensable gas and make it into nanobubbles. One key thing about the supersaturator that you need to remember is that it relies on an overnight resting period. What does that mean? What that means is essentially that we need a period of time where there's very little draw off or demand on the cold and the hot water system so that this system can regenerate nanobubbles in the tank, okay? That's what we need. Most institutional systems, most institutional buildings are not 24/7 operation, and even if they are 24/7 operation, they're often not running at a high demand 24/7. So as long as your building or your system that you want to apply this to isn't running in a high demand 24/7, this is a great setup to get nanobubbles into your system, okay? This system does generate nanobubbles constantly. All of our systems do because they all run on continuous circulation. So as long as this system is on, it's making nanobubbles. Okay, the nanobubbles are drawn off in the cold water and distributed into the buildings. Cool thing about this is that this is going to clean the cold water and the hot water and inhibit scale buildup, kind of like we talked about before. If you've got those point of use water heaters, or you've got, for instance, point of use mixing valves, or you've got point of use other devices out in the system that scale up, circuit setters, valves, things like that, and you're having scale problems in your cold water valves and appurtenances and things like that, this is a great setup because the other two setups we're going to talk about on the domestic hot water recirc return lines will not add any nanobubbles to the cold water. This is the only setup that we have that adds nanobubbles to the cold water. So let's jump in here and look at what we got going for this system. I'm going to walk it out for you, okay? Let me start with a pro tip here by telling you that some people have asked, and I've even seen some people try, to just install a nanobubble generator on the line coming in, okay? So this line up here, the cold water line, for instance, let's say you had a 2-inch cold water line coming in from the street going into your building. I've had people say, well, why can't I just take that nanobubble generator, just stick it right there in line? That way that cold water's coming in, it'll just make nanobubbles and go into the building. And I get it. That seems like a reasonable idea. But it won't work. And it won't work for a couple of reasons. First of all, you would only be getting one pass of water through there, which would make nanobubbles for sure. But by having a recirculated system, we feel that our experience tells us that constantly moving that water and, more importantly, that air through the nanobubble generator makes more bubbles. More bubbles means more work, means more scale removal, and you have better success. That's kind of the first problem. But the bigger problem is you have to understand the dynamics of a plumbing system, okay? This water is coming in at a certain pressure, and then that certain pressure has to push all that water all throughout the whole building, right? So let's say you have a building and there's no draw off, there's no demand, right? That's just sitting there at 70 PSI, let's just say. Now what happens is everybody starts opening faucets, right? And the water starts flowing through this line, okay? Well, it needs to stay at that same pressure because it needs to be able to go up to the higher floors. You know, flush valves, that when you push a flush valve on a toilet or on a urinal or something like that, it requires a certain amount of pressure when it flushes so that it can work properly. And domestic water systems and the water coming into the building is designed to stay at that pressure under a variety of flow conditions, okay? When we look back at what our nanobubble generator does, remember back to what we talked about. On a nanobubble generator, as the flow increases, like for instance, if we open a bunch of faucets and we go from 1 gallon per minute all the way up to 50 gallons per minute all of a sudden, if we were just running straight through a nanobubble generator, what would happen? We would have a significant drop in pressure because you can only push so much water through there. Remember, flow increases, pressure drop increases. So we would cause damage, and we would cause detrimental effects. You'd have a loss of pressure on the downstream side in the building, and it would just wreak havoc. So please do not install the nanobubble generator directly on the inlet line to the building, or even to the water heater. Okay, I've also had people say, well, this line just feeds a water heater. Can I put it on there, a feed water line, or to a feed water line to a boiler? Don't do any of that. That's never going to work. It's just going to lead to more problems. This is a much better setup. We've used this setup. You can see one of them over here in a dormitory environment, but this is the way to set it up, and let's walk through it. So we got our cold water coming in right here, right? Typically the cold water would come up here, come into the building, and then go like we talked about earlier. What we're going to actually do is take a branch line, come off the cold water, typically after the backflow preventer and after any sort of pressure reducing valve and after any sort of a meter. Okay, we're going to take a branch line down, and this is going to be the same line size as your main, okay? And when it comes to sizing a supersaturator, we will give you sizing. Just reach out to me. We'll give you sizing, but we size these based on the main line water size. So if you tell me you have a 2-inch water main, I'll tell you how many tanks you need and what size nanobubble generator you need, okay? So it's sized based on the water main size, okay? Now, so let's just say we work with a 2-inch water main for right now. So we have a 2-inch water main. We'd have a 2-inch line coming right down here. We're going to have a check valve right there. We're going to go into the top of our nanobubble tank, okay? What that's going to do is that's going to take cold water down here. It's going to fill this storage tank all the way up, right? Once this tank is full, then what's going to happen is the water is going to flow out this top tap, go right up this line right here, and right back into our system, okay? That valve up there, our bypass valve, when this system is in operation, that valve is completely closed. So all the water coming into the coming in from the street, going into the building, goes into the tank, comes out of the tank, goes up into here. That water will go into the whole cold water system, where it'll feed the brain, it'll feed the water heater, it'll feed the cold water fixtures, it might feed a cooling tower, it might feed a lawn sprinkler, it might feed a boiler water makeup. Everywhere where that cold water goes, you're going to have nanobubbles, and you're going to get the net effect of removing scale and inhibiting scale from those systems. So there are some additional upside benefits to putting a cold water supersaturator in for other pieces of equipment and pipes and things like that that don't come off of the hot water system. Okay, so that's how the cold water line works. Now, the way the supersaturator works is it has an independent, what I call a runaround loop, which is essentially we take off the bottom tap of the tank, we come out with a 2-inch line here, we run down through a strainer and a dedicated circulator pump. The good news is that even if this is a 2-inch water main, we can use a 1-inch nanobubble generator, because we're going to select this pump. When I say we, Armstrong will select this pump. Typically, we use a 30-gallon per minute pump, 110 volts, single phase, only needs a 20 amp outlet to plug in. It's very simple, just a single speed, constant flow pump that recirculates the water 24/7, right? We've got a check valve that runs over here, runs through our nanobubble generator with our pressure gauges, right? Comes up there. We've got a balancing valve. That's just if we need to add a little bit of extra reduction in flow. Okay, so when we select this pump, we select it for what we believe, how much piping you might have, because you're going to pipe all this in the field. We have an initiative to put all this into a skid-mounted package, but for now, what's going to happen is Armstrong will sell you the tank if you'd like, or you can purchase the tank from Supply House or something like that, and we'll sell you the nanobubble generator, and we will provide you with a specification and a couple recommendations on some pumps, an Armstrong and maybe a Bell & Gossett pump that we've used and we've seen used successfully that has the curve and the characteristics, but you're going to pick a pump out and supply that, and then a contractor or the owner is going to pipe all of this up himself based on the footprint that he has. You can kind of see this one here, and we have slide decks and photographs and pictures of these types of systems already set up where we can get you those, and you can kind of see what they look like. But essentially the way this works is this pump runs 24/7, circulating water in and out of that tank through the nanobubble generator. So as the fresh water comes in with non-condensable gases, it goes into this tank, right? Some of the water stays in that tank and it's constantly turned over and turned over and turned over. Those non-condensables get shredded and cavitated into nanobubbles, and we get a super concentration of nanobubbles in this tank, especially during this overnight resting period, okay? That's when we mostly make all that nano, is at night. Then during the day, as the water water comes in here. Remember, this valve is closed. Water comes in here, picks up those nanobubbles, sends those nanobubbles out here, out into the system, and then those nanobubbles do the work, right? These systems, no matter whether it's on a super saturator or it's on domestic hot water, they're going to work over time. We're giving a dose of nanobubbles into the system. They're going to work, and then, they're going to get depleted because you're going to draw the water off from the taps. Then we build them up again at night, and they get drawn off during the day. Okay, this is a very simple setup, works really, really well. We've had good success, especially where we've had point of use water heaters, okay? But this will treat the incoming water into the boiler or the hot water heater, into the mixing valve and things like that to keep all of those things descaled, okay? Now, the next thing we want to talk about here is our domestic hot water recirc return systems, right? So we can put it on the 120 side or we can put it on the 140 side. It really doesn't make any difference. Let's just talk through it on the 140 side, and then we'll talk a little about the 120 side. Let's just do a little refresher, right? So our cold water comes in right here, okay, goes into our hot water heater, comes out, we got 140 going across here through our laundry, right? Comes back down through here. Here's our circulator pump. Now, this pump right here becomes the heartbeat of this system. Remember what we talked about. This pump has to be functioning, and it has to be able to overcome that 5 pounds of pressure drop. Now what we're going to do is typically this pump would be pumping along here, all the way back around here and right back into the boiler. So all you have to do for this system is find a piece of, find a place in this run of pipe right here to put a branch line. Come up here, you have an isolation valve, Y strainer with a blowdown, and you can also do, like I mentioned, the automatic blowdown if you'd like, pressure gauges or a differential pressure gauge, nanobubble generator, outlet isolation valve, and you're all set, okay? Do the same thing on the 120-degree loop. It really doesn't make any difference, okay? Now, the way that this system is going to work is essentially you're going to close this valve off. When you start this system up, you're going to close this valve off to force a small amount of water to go through the nanobubble generator to get to the right flow rate, right? We try to target 100%, so that's why we need you to tell us what is the flow rate of this pump right here. Let's say that this was 10 gallons per minute. We would try to target 10 gallons per minute. One of the beauties of this side stream setup, though, is that, for instance, if your flow rate falls somewhere and it's not quite on our chart, like this is the chart for the ANG20, okay, and you can see that our ideal flow rate for the ANG20 right here starts at 2 gallons per minute, right? So you've got the 2 gallons per minute out of 5 pound pressure drop. You can run it with more flow rate, but you're going to have more pressure drop, right? And as you increase the pressure drop, then what you're doing is you're asking this pump to do more work, right? So the bare minimum that we're asking this pump to do is an additional 5 pounds of pressure drop, okay? But for instance, if it will do more, okay, and that's another beautiful thing about this setup, is just by opening and closing this bypass valve, you can actually affect what this pressure drop is right here. So essentially, as you close this valve, right, and you force more water through this nanobubble generator, remember, the more water that flows through here, the more flow rate, the more pressure drop we're going to have, meaning the more work that this pump is going to have to do, okay? But for instance, let's just say that we did have, let's say that this was a 10 gallon per minute setup, right? And we wanted to use an ANG20. The way that this would work is we would put this balance valve in here. Let's just say that, for instance, this was an 1.5 inch line right here, or a 2-inch line. Okay, and it's running at that. We would take a branch line here. We would go up here. This is a 3/4 inch. You can see up there, 3/4 inch. We'd run a 3/4 inch line over here, 3/4 inch through the ANG20, right? So we would close this valve right here, and we would watch for a 5 pound pressure drop between here and here. So if coming off of this pump, we had 45 pounds of pressure, right? We would start this system up. We would see 45 pounds here. And then what we would look for is we would keep closing this valve. And I did a whole video on starting one of these up, super, super simple. But if we had 45 coming in, we'd look for 45 here, and then we'd look for 40 here. Once we get to that point, we know we have the proper flow rate, which would be 2.2 gallons per minute. So in that case, if we had 10 coming out of this pump, 10's coming along here, 2.2 is going through here, the other 7.8 is going right through here, okay? So this one would have 7.8, this one would have 2.2. The net effect would be you'd have 45 on the inlet here, 45 on the inlet there, and 40 on the outlet here, and 40 on the outlet here, heading back to the system, okay? So that's essentially how the nanobubble generator works in this setup. And the way that this does is over time, essentially what's happening is, you fill up your hot water system, you start sending this water out, it's circulating through the nanobubble generator, coming back here, it's going through the boiler, it's going to pick up some heat, It's going to do some descaling in this boiler. It's going to head out. It's going to just keep going round and round and round. Again, this pump's running 24/7, so this is descaling 24/7. On your 120 volt or 220 degree circuit, it's the exact same thing. The difference is, remember that we're piping that line back to the return over here on the brain, okay? Now, on the filter side, we talked already a little bit about the filter. You can either add a filter or not, and that's where you would put the filter, is right there, side stream around the pump, where you come off the discharge, go through your filter, and right back into your suction side of your pump. And that would be the best way to pipe that up. Okay, let's talk now about startup and expectations. I kind of talked a little bit in the last segment about how you start those types of systems up. I'm going to back up for just 1 minute here and talk a little bit about startup. Okay, so for typical systems, you're welcome to just start them up and get them right up to the 5 pounds of pressure, which is the optimal flow rate, and let them run, okay? Depending on how much scale you have up and what kind of deposits you have built up in your systems, you can see different results. And we're going to look at some images here in a minute of different results that customers can have. We have no way to predict what those are going to look like, okay? And so we just want you to be aware that there is a process for starting these generators up, because they are going to work. They're going to remove existing deposits, and you're going to need to deal with those deposits in some way. Having these filters is a really good idea. Doing your blowdowns is a really good idea. Having your automated blowdowns is a really good idea. I will tell you that our experience over the last couple of years of starting dozens of these up and working with customers has told us that one of the best things that you can do is, when you initially start these generators up, is to do a lot of blowdowns, okay? Whether you're blowing down your plumbing fixtures out in the system, that would be good. But for sure, we want you blowing down your strainers that are in your mechanical room, whether you have strainers on your mixing valves, if you have a blowdown on your water heater, and also blowing down your strainers on your nanobubble generators, and if you have a strainer on your pump, okay? At least for the first few days, every single day, go and do a blowdown, right? And if you're getting an anemic blowdown, meaning that the blowdown is not coming out at a very fast rate, that's a good indication that your strainers are plugged. Go ahead and pull those bonnets off, check them, and clean those strainers out. So that's a good way to get the initial deposits when you first start these up. Some of the initial deposits can be kind of on the larger side, especially if you have corrosion and heavier, flakier scale, depending on, you remember we looked at those different types of mineral scale. They all kind of attach and look a little bit different. But I'm going to give you worst case scenario. I'm not trying to scare you away. I'm just trying to set expectations so that you can set expectations with your customer, okay? But blowdowns is a really good thing to do. Having a filtration setup is a really good thing to do, because that will help clean up those deposits. Typically, your mechanical room is down in the basement, so deposits typically follow gravity, right? You know, you don't often move all your deposits up to the top. You can, you know, the free floating deposits will float and they will move with the water, but something down in the basement of the building is typically the best place to put the filter. Okay, same thing holds true on the supersaturator on the cold water system. You're going to start that system up. It's going to start making nanobubbles, but you're going to want to, you're not going to do much blowdown at the supersaturator. There's no real reason to do any blowdowns, because again, you're just working with the cold water there. Okay, you're not going to get much blowdown there. You're going to need to blow down the system. Since you're not going to have this strainer, you're going to want to be blowing down on your domestic water circulator pumps, on your boiler, and on any other strainers that you have in your mechanical room. That's going to be your best friend, is to do blowdowns on that. Now, for my hospital customers and hospitality customers, or any customers who are potentially wary of deposits coming out into their shower heads or their aerators, hospitals won't have aerators, but hotels will have aerators, and they're very concerned about possibly discolored water, things like that. The good news is none of that stuff is toxic. It doesn't contain anything that's harmful, but it can be unsightly, and it can also cause some plugging up of those aerators. It can plug up shower heads. You can end up with some orange water. You can end up with some little flakes in the bowls of your sinks and stuff, and that may be objectionable. obviously to patients in a hospital or to guests in a hotel. So what we've devised to kind of overcome that is what we call a slow startup or a gentle startup, okay? And we have a full instruction sheet when we're working with customers like that we'll send you that kind of walks this out. But in a nutshell, the way that works is it's basically by introducing nanobubbles kind of gently, a little bit at a time. So rather than turn this thing on full blast and just walk away and let it rip, what we do is we actually have you start with potentially a 1 pound pressure drop between these two gauges. So making less nanobubbles, lower flow makes less nanobubbles, higher flow makes more nanobubbles. So we might have you set this up at a 1 gallon per minute and just start like that and have the customer be very sensitive to observing and looking for any downstream issues that they have. And if they do, then opening this back up and backing it off. That's one strategy that we've seen work successfully. Another strategy we've seen is to go ahead and open this up to the optimal flow, run it, say, for 1 day, and then shut it off. Basically, shut this valve off, open this valve wide open, and let the nanobubbles kind of just work in the system a little bit, but let them get diluted with more fresh water, less nanobubbles. By having this side stream setup, that's very easy to do. So, for instance, if a customer, any customer, first started this up and they were experiencing some issues where they're like, this is a little bit too aggressive, that's exactly what we would want you to tell them to do, is to go ahead and open this bypass valve up. You know, you could still leave water flowing through the nanobubble generator, but open this bypass valve up so less water goes through the generator. If you're using a super saturator, okay, what you could do is open the bypass so that you get a blend of some super saturator water and some tap water, so it kind of blends together. But we have instructions, we can work with you. I don't want you to be afraid of this technology because it's only in the beginning, the first few days, okay? This isn't something where, for instance, you install this and for 6 months or a year, every day or every third month, all of a sudden hiccup, a whole bunch of nasty stuff comes out and it's really unsightly. The reports we've heard are few and far between, but the ones we have heard have said, hey, it's only the first few days and then it goes away and we don't see anything that's objectionable. Because we know once you remove the loose stuff, then the actual removal of the more tighter packed stuff is all microscopic. You can't see it in solution. It doesn't cause any unsightly problems. But let's take a look at what some customers have experienced so far, okay, in their systems. So this is a startup on a system right here. And this is what I would say is probably worst case scenario. I'm going to show you worst case scenario first. Again, I told you, this system right here, you can see they've got some iron oxide deposits, maybe some biofilm and different things. This is an aerator off of a faucet in a hospitality setup. They got some chunks of scale, some chunks of debris and things like that. Okay, and then those types of things can end up in the sink here as well. That could have ended up there, or it could just be that they cleaned the aerator out in the sink. Chances are they may not have had that like that. You could have some discolored water like this. Again, this is worst case scenario. Please don't scare your customers away. Not every customer experiences this. This is just the worst case scenario, right? Here's a good example of a contractor who on a bag filter setup, remember we can put those bag filters on the recirc return line. Essentially what they made was this little holder here and the bags are dropped in there, right? Those bags are about this long. That's what you're looking at, kind of the top down. And what you're kind of looking at here is here's a brand new clean bag and you can't quite see the dates down here, but they kind of have the dates. And this is great. This is exactly what I would recommend you do for any delayed billing or try before you buy, or I want you to prove it to me somehow before I pay for this and believe in it. This is exactly how to do it right here. Start with a clean filter. Again, after you've run that filter clean without nanobubbles, and then just observe it over time. And I love how they pulled it out. They stuck it in there. They pulled this one out. They stuck it in here. And you can see over time, and we're going to look at a few more bag filters, the stuff that gets removed, the scale, the sediment, everything that's coming out of the system due to adding the nanobubbles into the system. Here's another example of some blowdown water. This is what you can expect to get out of your blowdown water in any type of a system that might have galvanized pipe or stainless steel pipe or any sort of ferrous metal pipe. You may get some orange water that looks like this in the beginning, okay? This is worst case scenario. This is not how it always happens, okay? Next thing I want to show you is, again, here's a great setup of bag filters. You can see they've got their recirc pumps here and their bag filters right next to it. This is beautiful. This is before, brand new bag filter, and this is after, okay? This is a client who wanted to do their own testing, and this is actually the client where we showed you those pipes where over the 8-month period, the pipes got less and less and less scale. That's this customer. And that scale that came off the inside of those pipes, this is where it ended up, was in these bags. And they were able to see it from clean all the way up until they see the scale. And you can turn those bags inside out and get the scale out of it and everything else. Again, this is the way to prove it out to a customer so they can see exactly what it is. If they're not willing to cut their pipes open, this customer was so willing that they cut their pipe open as well as installing these because they really wanted to vet whether or not the technology works. Now they're on board and they're budgeting to buy more nanobubble generators. Here's an interesting example of what also can happen. So this is a system where on the domestic hot water recirc return, nanobubble generator was installed, and we didn't get a lot of feedback from the customer until about a year later. So a year after installing it, the customer called the rep up and said, hey, my brain is going burp, 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 hunting all over the place, right? We know that what that means is essentially no flow. If a brain is doing this, that means there's no flow more than likely, right? Rep went out, pulled out the return. So this is the return strainer from the system, and you can see the buildup of scale that's been built up on the screen of the strainer. And then when you bang it off, you can see all that scale. So that's all scale that's been removed from the system, made its way to the strainer on the brain package. Now, it presents itself as, oh, my brain is hunting all over the place. I'm bothered by that, right? That's what a customer might think, but the reality is this is exactly what you want to see, okay? This is evidence that we removed that scale, that we have bonded with those minerals in solution, and they brought them to this point where eventually they dropped out and were filtered out on these particular screens, okay? Another reason why it's super important that you actually open and pull these screens out of your strainers, because you can't flush that out. Doing a blowdown is not going to remove a scale deposit like that. Okay, here's another great example. Okay, this customer had shell and tube heat exchangers, okay, hot water heater shell and tube heat exchangers, where essentially what you've got is you've got steam inside of the tubes and you've got domestic water on the shell side. This particular customer had a whole bank of these water heaters, and essentially their water is so hard that they're building up this lime scale buildup, which you can see here. You've also got some biological buildup and some different things in here to the point where that water wouldn't even flow through there, right? And you can just imagine the steam inside of there is getting hot, but it can't really heat up that water. This customer was really in a pickle because they essentially had to replace these heat exchangers every 6 to 9 months at a tune of $17,000 a piece for each one of these heat exchangers, okay? When we did this project for them, we put the nanobubble generator in and we just ran nanobubble through this water, and this is the before and the after of just nanobubble water. Pretty amazing results. Okay, here's some other examples of some things to look for, places where you can see the results, okay? On your DRVs, okay, when you have buildup on different components of the DRV, you know, those of you that service DRVs will know all about this, but we see the DRVs cleaning up, you know, this is a great before and after setup as well for customers that are trying or kind of skeptical. If you can pull a brain out, if you're servicing a brain and you see a lot of buildup of scale on these components, take pictures of that, put a nanobubble generator in, then come back in 3 to 6 months and you'll see it. It'll actually clean up and remove all those deposits. Same thing over here on your shell and tube heat exchangers. A lot of times you're going to have scale buildup both on the tube sheet and where the tubes meet the tube sheet, and then down inside the tubes as well. If you can stick a borescope camera down in there and take pictures of that, that's super helpful as well to be able to look at that, or if they're doing some sort of eddy current testing to see if they have corrosion or buildup or different things on your shell and tube heat exchangers. Any type of data like this is great to have. Photos like that, please send those to us. We love to see those types of photos, the before and after photos. Same thing on other types of heat exchangers. Any type of heat exchanger that you can open up and look in beforehand, or even look at it, you know, you can assume that it's clean, and then after 6 months or a year, look in there and see what it looks like. And we see some great results from nanobubbles. Here's a good looking picture right here. Okay, so here's your before. Like I said, a lot of scale and goop and goopy stuff built up on the tube sheet here down into the tubes. It's kind of dark, you can't see. You can see a little bit of it down in here. But the cool thing is if you look at this one here, it doesn't look like there's a whole lot of difference, but this is only a few months of difference time between this is the start and this is just a few months later. And actually you're starting to see some things, right? We can start to see the metal here. Over here you can really start to see the metal, right? And down inside of there, you can start to see the metal. Down here, you can start to see the metal as well. Those are all good signs. Those are good signs that that scale is getting removed. Again, this is a slow process. This is not like doing a rid lime clean in place where you're going to blast that thing out with acid and completely clean it out, okay? That's not what nanobubbles do. They don't work like that. They work slowly over time, okay? Here's another great example right here of a fluorite, okay? So you're looking down into a fluorite, right? Here's the before picture. You can see a lot of buildup right here on the on this surface here. What I really want you to pay attention to is this buildup back here, right? See this buildup back here, and also this buildup right down in here, right? Here's an after photo several months later, and you know it doesn't look significantly different. But what I see are, you know, we're starting to see some of the metal here. We can start to see some of the metal over here. But this is what I really like, is I'm really starting to see a lot of metal here, and I'm already starting to see a lot of metal right here. So we can be able to look at this and say we can see that the nanobubbles are actually removing that scale, and that's going to keep this fluorite. If you know fluorites, you know that these babies have challenges with scaling and things like that. So this is going to help this customer keep this fluorite working well, staying on temperature, and being more efficient, not having to rebuild these heads so often and things like that. Here's a beautiful example, right? So here's a completely plugged, holy cow, that's a lot of scale piled up into a strainer, right? We've seen situations where you've got that much kind of scale built up in there, go all the way to completely clean, right? So this is what they were getting prior to nanobubbles. This is what they can be expecting to get after nanobubbles, all right? Just a little bit of buildup in the strainer basket versus a significant amount. Also, what I will say is when you first do your initial startup, you could get a strainer that full. That's why we want you to do those blowdowns. By doing blowdowns, and I'm talking about doing an observed blowdown, not just go down there and blow it down and walk away. Go down there and open it up, blow it down, and look at what the water stream looks like. And if it doesn't look like it's coming out at a high velocity, you got to open it up and look inside of there. So those are some of the expectations on startup. Your results might be different. It just kind of depends on what your deposits are. We're still learning what different deposits look like, but we've seen very significant results. I really highly encourage you to use cartridge filters, use those bag filters so that you can look at the scale over time. Again, on any delayed billing type of a situation, one of the requirements to qualify for that program is that you do install a filter on that system so that you can observe those results. Thank you.